everyone. Welcome to Management Science. This is your instructor, Giselle H. Raz, and today we'll discuss linear programming, its concepts and applications in business. So if you're ready, let's start. So before we begin our discussion today about linear programming, we'll have first a short activity about pizza and burger. So I call this pizza versus burger. So these are your favorite snacks, right? So let's assume that pizza and burger would need the same ingredients to make a unit, or one pizza or one burger. So let's assume that pizza would need two pieces of dough, three pieces of meat, and then one piece of veggies, and then two pieces of cheese. I know it sounds awkward, but let's just assume a pizza would need veggies, okay? So on the other hand, burger would need one piece of dough, one piece of meat, two pieces of veggies, and then three pieces of cheese. So again, this might not be the actual burger and pizza you're thinking, but let's assume that these are the ingredients for both pizza and burger with different quantity requirements. Okay? So a unit of pizza would sell 100 pesos, and then a unit of burger would sell 75 pesos. Okay, so let's also assume that we only have a limited ingredients. We have limited resources. And the available resources we have is that for dough, we have only 23 pieces. For meat, we have 30 pieces. And veggies, we have 25. Cheese, we have 41. So, how many pizza and burger do you think would be produced out of these resources given the quantity requirements for dough, meat, veggies, and cheese for the making of pizza and burger? So you can pause this video and get your paper, solve the problem, and then go back to this video and then let's see if you got the right answer. Okay? So please pause the video. So, how many pizzas and burgers have to be produced and sold? Did you get the correct answer? Do you think you got the correct answer? Okay. So, actually, we need to produce and sell seven pizzas and nine burgers to maximize our limited resources. Did you get it? I hope so. So, our objectives in this lesson is that for you to be able to understand linear programming and its wide application in our real world situations, and design a model for linear programming, and apply and resolve basic problems using linear programming. So, if you're ready, let's jump in. So, what is linear programming? Linear programming is a model that consists of linear relationships representing a firm's decisions given an objective and resource constraint. So, in linear programming, we're actually allocating our limited resources to maximize our profit or minimize our cost. It is not uncommon for a business organization to only have a limited resource. Say, for example, limited number of people or limited number of employees to do the job. So, how do organizations maximize their profit or minimize costs given that they only have a limited resource? Okay, so linear programming could be a great tool to help the management resolve their problem when it comes to limited resources allocation. A linear relationship means the interdependence of one variable, called the independent variable, and another variable called the dependent variable. This means that a change in the independent variable will affect the dependent variable. Linear programming also helps managers determine solutions, for example, to make decisions for problems to achieve some objective in which there are restrictions such as limited resources or a recipe or perhaps production guidelines. So, linear programming is actually a tool or a technique that is widely used in different organizations wherein there are limited number of resources and they need to maximize profit or to minimize costs. So, in short, linear programming is all about allocating limited resources to achieve the objective, which is either to maximize profit or to minimize cost. Okay? Now that you have understand what linear programming is all about, let's proceed to the application and limitations of linear programming in an actual business. So, linear programming can be applied in the production of goods which require similar products or similar raw materials, like what we did in the pizza versus burger, wherein the pizza and the burger need the same ingredients but different quantities of ingredients to be specific. It can also be applied to decision makings wherein the company is to decide whether to sell now or process further. For example, in the case of log production, wherein the company is supposed to decide whether to sell now the logs, the raw logs, or to process further to make wood products such as table or chair. Linear programming can also be used in decisions wherein the question is which is to produce and how many to produce, decision making. However, despite the wide application of linear programming in business, it also has its own limitations. For example, in linear programming, there is a high reliance in the linear relationship between the variables. And this could not be entirely true because in an actual real world scenario, there might be some instances or certain cases wherein the linear relationship might not be true to all situations. And it does not consider other unknown variables such as contingencies or losses, shrinkages, and wastes. So these are limitations of linear programming. Despite the limitations, linear programming is still widely used in business situations, particularly in the allocation of resources which are limited and scarce. Okay, so it also does not consider increases in and decreases of the demand, such as the company will just produce and produce and produce and not consider on the demand, then it's also a limitation. So in the given activity, what was your observation? What was our primary objective? So our objective in the given activity was actually to determine the number of pizza and burger to be produced and sold so that we will maximize our profit. That was our very objective. And then the resources given, there were actually four, and that is the dough, the meat, the cheese, and the veggies. Okay, so these ingredients are actually limited, hence the constraints. So the constraints that the ingredients given are only limited in number, and we have to maximize these resources so that we will achieve our objective, and that is to have a maximum profit. And our decision was to produce and sell seven pizzas and nine burgers. Okay, so in our everyday lives, what are the common decisions we make where our resources are unlimited? So there are many situations or instances in our everyday lives we are confronted with, and then we only have limited options or resources, or so for example, in every day we only have 24 hours, and then in that 24 hours we need to allocate 8 hours for sleep, so we only have 16 hours to do things. Okay, so out of these 16 hours we have to maximize the use of these hours so that we will achieve the maximum benefit out from it. So we can afford to lose any time by doing nothing, or by just wasting our time or hours in doing nonsense things. Okay, so this time is limited, and that we need to maximize the use of it so that we will benefit the most of the resources that we have. Okay, so in the activity given, what were the independent variables? So when you say independent variables, these are variables that do not depend on other things. So in the problem, in the activity, our independent variables is the number unit requirements per pizza and burger. So it's only fixed. So for example, we need two dough for pizza and then one for burger. So it's fixed and it can't be adjusted. Okay, so these are independent variables. And what were our dependent variables? The dependent variables were the number of pizza and the number of burger to be produced. So these are dependent because this depends on how many resources are available, right? There is actually a logical steps or techniques on how do we resolve linear programming problems, such as in the case of pizza and burger. So our first step is to define the decision variables. When we say decision variables, what are the items or the variables given? For example, in our case, how many pizza and burgers do we produce? This is our decision variables, the pizza and burger. Okay, so the second step is to define the objective function. So what is the objective of the problem? To maximize the profit. Okay, so and next will be to define the constraints. What are the constraints? The resources, since the resources are limited. So we have the dough, the meat, the veggies, and the cheese available. So these are the first three steps in linear programming. So in our problem, for example, defining the decision variables are mathematical symbols that represent levels of activity. The decision one has to make in the activity is how many pizza and burgers to produce and sell. And these are the quantities to produce and can be represented symbolically as, let's say, for example, X as the number of pizza to be produced and sold, and Y the number of burgers to produce and sell. So that's for these are our decision variables, the X and Y. Again, X represents pizza and Y represents the burger. Okay. Step two, defining the objective function. So again, our objective is to maximize our profit. In linear programming, objective function is a linear mathematical relationship that describes the objective of the firm in terms of the decision variables. So the objective function is always consist of either maximizing profit or minimizing the cost or some values. So normally, these are the two objectives in linear programming, to maximize or to minimize. So in our case, we have to maximize the profit. So in the activity to derive the objective function, we must first calculate the profit per pizza and burger. Since we are given the selling price and the cost, then we need first to derive and compute the profit per pizza and burger. So we have the ingredients of this is for the pizza. Okay, so for every unit of pizza produced, we need two pieces of dough, three pieces of meat, one piece of veggies, and then two pieces of cheese. A total of 75 pesos. So this is our cost. Okay, so just multiply 2 pieces times 10, so 20, and then 3 times 12, and so on. So total cost of 75. So if our pizza is sold at 100 pesos and our cost is 75, therefore the profit per unit of pizza produced and sold would be 25 pesos, right? So after we have computed the profit of pizza, now let's have the profit per burger. So the cost per burger is computed as follows. So again, for every unit of burger, we will need one piece of dough, one piece of meat, two pieces of veggies, and then three pieces of cheese. So just multiply the number of units and the cost per unit. So we would have a total cost of 54 pesos. And let us remember that per unit of burger would sell for about 75 pesos. Thus, if the selling price 75 and then the profit would be 21 pesos given the cost is 54. Okay? So now we have already the profit per pizza and the profit per burger. So next step is to determine our objective function. So with the given variables of x as the number of pizza and then y as the number of burgers produced and sell, our objective function is represented as follows. So we have the z is equal to 25x and 21y. This can be interpreted as to maximize z. Z is our maximum profit. Okay, so it's equal to the 25. This is the profit per pizza, 25 pesos, and then plus 21y. 21 is the profit per burger, and y is the burger. Okay, so we have to maximize the profit z. So again, 25 pesos is the profit per pizza, and 21 is the profit per burger sold. So step 3 is to define the constraints. Constraints are the restrictions or limitations in achieving our objective, that is to maximize the profit or minimize the cost. So in our activity, there were four resources used for production: the dough, the meat, the veggies, and the cheese, all of which are limited. So the production of pizza and burger requires all four resources. Okay, so all the both pizza and burger would need these four resources. So we have here, for again, the pink colored uh, cells are actually the pizza, and the yellow colored cells are the burger. Okay, so the pizza would need two pieces of dough, three pieces of meat, and so on, and also the burger. Also, we need to understand how many resources available do we have. So we are given that in total, the dough only have 23 pieces, and the meat have 30 pieces, and then the veggies 25, cheese and 41. So this is the total number of units per ingredient available. And we need to allocate these ingredients to maximize our profit. So each resource is limited, and we have to utilize most of them to maximize our profit. These can be represented as follows. So for example, in the case of the dough, we will have 2x plus 1y lesser than or equal to 23. So 2x, remember that x is the pizza or represents pizza, and then 2x because each pizza requires 2 dough. Okay? Then we have 1y because each burger, which is the y, requires 1 dough. The inequality sign, we have the lesser than or equal sign, okay, represents the allocation of all dough, which can be or may be lower or equal to the total available dough, but not more than 23, of course. And then the 23 is the total available dough, which will be shared or allocated by the production of the pizza and the burger. Okay? So this constraint or equation is only for the dough. Hence, for the meat, we'll have 3x plus 1y equal or lesser than 30. And for veggies, this is 1x plus 2y equal or less than 25. Remember again that x is the pizza and y is the burger, which means to say 1x plus 2y. This means that one uh, 1 unit of pizza would need one veggie, and then 1 unit of burger would need two veggies, equal or lesser than 25. This is the total number of veggies available. And lastly, for the cheese, we have 2x plus 3y is equal to or lesser than 41, the total number of cheese. So, final restriction. When you say final restriction, the number of pizza or the x and the burger or y must be equal to 0 or any positive number, because it is impossible to produce negative items. Okay? So these restrictions are referred to as non-negativity constraints and expressed mathematically as x must be lesser or must be greater or equal to 0, and y must be equal or greater than 0. Again, the x or the pizza cannot be a negative number, and then y also cannot be a negative number. Hence, it should be greater than or equal to 0, because it's impossible for us to produce a negative pizza or negative burger, right? So hence, the complete linear programming model for this problem can now be summarized as follows. So this is now the entire linear programming model for our activity. First, we have the objective function of maximize the z, or maximize the profit, which must be equal to 25, the profit per x, or the profit per pizza, plus 21y, or the profit per burger. Subject to constraints, we have the dough, 2x plus 1y greater than or lesser than or equal to 23. And then for meat, we have 3x plus 1y, which must be lesser than or equal to 30. For the veggies, we have 1x plus 2y, which must be lesser than or equal to 25. And then cheese, we have 2x plus 3y, which must be lesser than or equal to 41. Okay? And we have also have our final restriction, which is the x, or the pizza, should be greater than or equal to 0, but not negative, and also same as the y. So this is now the entire linear programming model for our problem. So after we have determined the model for linear programming, let's assume hypothetical values. Let us say that the value of x, or the pizza, is 5 and the value of y is 7. Okay, so thus let's use the dough constraint. Our dough constraint is 2x plus 1y is equal or lesser than 23. So we have 2 times 5 plus 1 times 7 is lesser than or equal to 23. So this is 17 is equal to or lesser than 23, which is actually correct. It's correct because 17 is lesser than 23. Okay? While it is true that x is equal to 5 and y is equal to 7 could be the solution to the problem, still it will not achieve our objective, and that is to maximize our profit, since there are still 6 dough remaining. Okay, so while if we produce 5 pizzas and 7 burger, while it could be the possible answer or the feasible solution, but it does not maximize our profit because 23 minus 17, we still have 6 dough remaining, okay? And we could produce something out from that. So let's assume again that the value of x is 8 and the value of y is 11, meaning to say we will produce 8 pizza and 11 burgers. So still using the dough constraint, 2x plus 1y is equal to or lesser than 23. So we have 2 times 8 plus 1 times 11 is equal to or lesser than 23. We will have 27 is not actually correct. Hence, if we will produce 8 pizza and 11 burger, it could be a false or a not the possible solution because it would exceed the number of total dough available, in which we would need 27 dough and we only have 23 doughs available. So this 8 and 11 is not the possible answer. Okay? So our solution, okay, so we'll have the substitution method. The constraint equations are solved simultaneously at the optimal extreme point to determine the variable solution values. So we will use two constraints to calculate the possible value of x and y. So let us say the dough and the meat. Okay, so we will use, there are four constraints and then we'll just use two of them. Okay, so first, we will convert the lesser than or equal sign to an equal sign. We will convert the inequality sign to an equality sign. So then we would have 2x plus 1y is equal to 23 and 3x plus 1y is equal to 30. Okay, so after we have converted the two equations, next is to compute for either x or y using the given equations for both equation. So we have 2x plus 1y is equal to 23. Let's assume that we will first solve the y, okay? So 3x, same, plus 1y is equal to 30. Hence, we will get y is equal to negative 3x plus 30. Now, the next thing is to solve the problem simultaneously through substitution. So we will now combine the two equations. The negative 2x plus 23 is equal to negative 3x plus 30. Okay? So we just combine the two equations. Then we can now solve for our x. So let's transpose. So the negative 3x to the left side, we will now have the negative 2x plus 3x is equal to negative 23 plus 30. Hence, the x is 7. Okay, so using this 7 as our x, we will now solve for the value of the y. So this is the number of pizza to be produced and sold, the 7. Now let us solve for the value of y using the value of x given. Computed, we have 7. So using the dou constraint, you have 2x plus 1y is equal to 23. Hence, we will get 2 times 7 plus y is equal to 23. This becomes 14y. 14 plus y is equal to 23. And our y is now 9. So this 9 is the number of burger to be produced and sold. Okay, so we now have the number of pizza, which is 7, to be produced and sold, and number of burger, which is 9, to be produced and sold. So this is now our solution. Okay. However, let's use the other two constraint equations whether we will get the same answer. Okay. So for the veggies and cheese, we have 1x plus 2y is equal to or lesser than 25, and for the cheese you have 2x plus 3y is equal to or lesser than 41. So our first step again is to convert this inequality sign to an equality sign. So this becomes 1x plus 2y is equal to 25, and we will get we'll transpose, no? So it becomes 1x equal to negative 2y plus 25. Okay, so now we have the value of x. Okay, so for the other equation for the cheese, we have 2x plus 3y is equal to or lesser than 41. So again, we'll have to convert this from an inequality to equality. So this becomes 2x plus 3y is equal to 41. And 2x is equal to negative 3y plus 41. And then we have negative 3 over 2y and then plus 41 over 2. Okay, so after this, we would combine the two equations. So the next step is to combine the two equations. So we have x is equal to negative 2y plus 25, and another equation of x is equal to negative 3 over 2y plus 41 over 2. So if we would combine these two equations, this becomes negative 2y plus 25 is equal to negative 3y over 2 and 41 over 2. So I intend not to remove the denominator, the 2, so that we could easily solve this problem by multiplying both sides with 2. So our next step is to eliminate the denominator 2. So to eliminate the denominator 2, we would multiply both sides by 2. So this becomes positive 2 times negative 2. That becomes negative 4y. And then 2 times positive 25. So we would get positive 50. And since we will also multiply the right side by 2, this will eliminate our denominator 2. So finally, we would get negative 4y plus 50 is equal to negative 3y plus 41. Now we would combine the equation. We will transpose the negative 3y to the left side. So this becomes negative 4y plus 3y is equal to negative 50 plus 41. And we would get 9 as the value of y. So take note that this result is also the same result as what we get in our previous discussion in the previous two constraints. Okay, so let's prove again that we will have the same number. So the y here is actually the number of burgers. So now let's solve for the number of pizza. So to determine whether the values of x and y are correct, we will test the values with the constraints equations. Okay, so the dough, we have 2x plus 1y is equal to or lesser than 23. And for the meat, we have 3x plus 1y is equal to or lesser than 30. And the veggies and the cheese. Okay, so and also the final restrictions, which we have the x and y should be greater than or less or equal to 0. So these are the above constraint equations. So we will test the 7x as our x and then y as our 9 as our y. So you will test if 7 and 9 is really the correct answer. So let's try each constraint. For the dough, okay, so we get, so 14 plus 9 is actually lesser than or equal to 23. This is actually true. Okay? And for the meat, we have 3x plus 1y is equal to or lesser than 30. So we have 7 and 9. 3 times 7, 21. And then 1 times 9 is 9. And then we have 30. So this is also true. Okay? So for the veggies, we have 1x plus 2y is equal to or lesser than 35. We have 1 times 7 and 2 times 9. We have 7 plus 18. So again, this is true. For the meat, for the cheese rather, we have 2x plus 3y is equal to or lesser than 41. So we have 2 times 7 and 3 times 9. So we have 14 plus 27 is equal to or lesser than 41. Again, this is true. Therefore, for the four constraints, the 7 and the 9 are actually correct. Okay, so since the constraints are all satisfied, it is now time to compute the maximum profit. Let's go back to our objective function. Again, our objective is to maximize our profit, the z. So 25 is the profit per pizza and 21 is the profit per burger. So by substituting 7 and 9, we would get a maximum of 364 pesos as the maximum profit of this problem. Okay? Final thoughts. Linear programming can be very useful in a lot of ways, especially in allocating limited resources. Okay, so you will encounter one day certain or many problems about allocating limited resources, and linear programming could be a very useful tool in resolving these kind of problems. It can also be resolved using a lot of methods such as graphical and simplex methods. However, we will not discuss the graphical and simplex method in this course because it will be discussed in your other subjects in mathematics. So for this purpose, we only discuss the substitution method, which is useful especially in our profession, the accountancy. So what we did is actually the substitution method. Okay? So I hope you learn a lot from this discussion. And I hope you will watch the next videos. Thank you for watching.